NVIDIA deep dives into Blackwell infrastructure. NVHBI used to fuse two iGPUs together, 5th general tensor cores, 5th gen NVLink and Spectrumx detailed. NVIDIA has given a deep dive into its Blackwell I platform and how it leverages a new high-bandwidth interface to fuse two GPUs. NVIDIA Blackwell GPUs with NVHBI, 5th general tensor cores for I, 4th gen NVLink, Spectrumx and more detailed at Hot Chips last week. NVIDIA announced that it was sharing more information on its Blackwell I platform while sharing the first images of Blackwell up and running at data centers. Today, the company presented its latest details regarding the whole Blackwell platform, which doesn't comprise one chip but uses several different products such as Blackwell GPU, Grace CPU, NVLink switch chip, Bluefield 3, ConnectX 7, ConnectX 8, Spectrum 4, Quantum 3. The whole NVIDIA Blackwell I platform is powered by over 400 optimized CUDA-X libraries that offer maximum performance on Blackwell chips. These libraries target diverse application domains and are built on decade-long innovations, stacked within the CUDA-X package. The library supports an ever-expanding set of algorithms, making it future-proof for the next generation of I models. So let's talk about Blackwell. The chip has 6 main building blocks: the I superchip with 208 billion transistors, the transformer engine which supports FP4/FP6 data formats through its tensor core, a secure I engine with full performance encryption and 5th gen NVLink which scales to 576 iGPUs, a RAS engine with 100% in-system self-test capabilities and the decompression engine with a 800 GB per second bandwidth. I superchip, 208 billion transistors, TSMC 4MP, and GT, 1600 square millimeters. Transformer engine, 5th general tensor core, FP4, FP6, FP8 data formats. 5th generation NVLink, scales up to 576 GPUs, 1.8 terabytes per second bandwidth. NVHBI, NVIDIA High Bandwidth Interface -10 terabytes per second bandwidth die-to-die interconnect. RAS engine -100% in system self-test. Decompression engine -800 GB per second bandwidth. Secure I, full performance encryption and The NVIDIA Blackwell GPU itself features the highest I compute, memory bandwidth, and interconnect bandwidth ever in a single GPU. The GPU utilizes two radical-limited GPUs merged into one using NVHBI, which we will get to in a bit. The chip itself features 208 billion transistors packaged on the TSMC 4MP process node in a NGT, 1600 square millimeters design. The Blackwell I GPU offers 20 petaflops FP4i, 8 terabytes per second memory bandwidth, 8 site on HBM3E, 1.8 terabytes per second bidirectional NVLink bandwidth, and a high-speed NVLink C2C link to the Grace CPU. NVIDIA's journey into multi-die architectures started with Ampere. Although not a traditional MCM design, the two GPU blocks were fused in such a way using a high-bandwidth interconnect that the chip had no differences from a monolithic implementation. This design was further refined over the coming generations, and with Blackwell, the company moved towards a two-die implementation. The chips were fused using NVHBI, NVIDIA High Bandwidth Interface, which offers 10 terabytes per second of bidirectional bandwidth across the single edge, consumes very low energy per bit, delivering a coherent link between GPUs that's both great performance and no comprise solution. The Blackwell GPU architecture is also supercharged with the 5th generation tensor core architecture, which comes with new microtensor scaled FP formats such as FP4, FP6, and FP8. These microtensor scale factors are applied to fixed length vectors, enable mapping of elements to scale factors that are fixed, and deliver wider FP range, amplified bandwidth, lower power, and finer granularity quantization. Looking at the performance implications of the 5th general tensor cores, each of the existing data formats, FP16, BF16, FP8, sees a 2x speedup per clock per SM versus Hopper, while FP6 delivers a 2x speedup over Hopper's FP8 and FP4 delivers a 4x speedup over Hopper's FP8 format. In addition to the new formats, Blackwell iGPUs also feature increased operating frequencies and SM counts versus Hopper chips. One of the newest features for Blackwell is NVIDIA Quasar quantization, which takes low precision formats such as FP4 and converts them into high accuracy data using optimized libraries, HW and SW transformer engines, and low precision numerical algorithms. Compared to BF16, quantized FP4 offers the same MMLU scores in LLMs and the same accuracy across Nemotron 415B and even 340B models. NVIDIA Blackwell brings together multiple chips, systems, and NVIDIA CUDA software to power the next generation of AI across use cases, industries, and countries. NVIDIA GB200 NVL72, a multi-node, liquid-cooled, rack-scale solution that connects 72 Blackwell GPUs and 36 Grace CPUs, raises the bar for AI system design. NVLink interconnect technology provides all-to-all GPU communication, enabling record-high throughput and low-latency inference for generative AI. The NVIDIA Quasar quantization system pushes the limits of physics to accelerate AI computing. NVIDIA researchers are building AI models that help build processors for AI. Another big aspect of the NVIDIA Blackwell AI platform is the 5th-gen NVLink, which connects the entire platform using 18 NVLinks with 100 GB per second bandwidth each for 1.8 TB per second bandwidth and X2 at 200 Gbps PAM4. There's also the 4th-gen NVLink switch chip, which is configured within the NVLink switch tray and feature a die size of over 800 square millimeters, TSMC 4np. These chips extend NVLink to 72 GPUs on GB200 NVL72 racks, offering 7.2 TB per second of full all-to-all bidirectional bandwidth over 72 ports and sharp-in network compute of 3.6 flops. The tray features 2 of these switches with a combined bandwidth of 14.4 TB per second. All of this comes together in the NVIDIA GB200 Grace Blackwell Superchip, an AI computing powerhouse with 1 Grace CPU and 2 Blackwell GPUs, 4 GPU dies. The board features NVLink C2C interconnect and offers 40 petaflops of FP4 and 20 petaflops of FP8 compute. A single Grace Blackwell tray comes packed with 2 Grace CPUs, 72 cores each, and 4 Blackwell GPUs, 8 GPU dies. The NVLink spine is then used in GB200 NVL72 and NVL36 servers, which offer up to 36 Grace CPUs, 72 Blackwell GPUs, all fully connected using the NVLink switch rack. This server offers 720 petaflops of training, 1,440 petaflops of inference, supports up to 27 trillion parameter model sizes, and bandwidth of up to 130 TB per second, multi-node. Lastly, there's SpectrumX, which is the world's first Ethernet fabric built for AI and comprises 2 chips, the Spectrum 4 with 100 billion transistors, 51.2T bandwidth, 64x800G and 128x400G ports, and the Bluefield 3 DPU with 16 ARM A78 cores, 256 threads and 400 gigabits per second Ethernet. These 2 AI Ethernet chips come together in the SpectrumX 800 rack, which is an end-to-end platform for cloud AI workloads. Combined, NVIDIA's Blackwell AI platform brings a 30x real-time inference uplift over Hopper while offering a 25x uplift in energy efficiency. But NVIDIA is just getting started. After Blackwell, the Green team also plans on launching its Blackwell Ultra with increased compute density and memory in 2025, followed by Rubin and Rubin Ultra with HBM4 and brand new architectures in 2026 to 2027. The whole CPU, networking, and interconnect ecosystem will also receive major updates throughout 2025 to 2027.